deep in one of the world's harshest environments, where rainfall barely reaches 100 millimeters a year, and summer heat regularly climbs past 45 degrees Celsius, the nation of Israel transformed an impossible dream into concrete reality. They built what many called the audacious folly of the century, a system of waterways stretching thousands of kilometers across barren wasteland, bringing life where none should exist. But this wasn't just about digging trenches through sand. This was about reimagining how a country survives when nature offers almost nothing in return. The Negev region, covering more than half of Israel's total land area, had remained largely uninhabitable for centuries. Temperatures could reach deadly levels during summer months, while winter brought only scattered rainfall that evaporated almost as quickly as it fell underground. Water sources that had sustained small communities for generations were disappearing year after year as demand outpaced natural replenishment. Yet just beyond the desert's edge lay the Mediterranean Sea, holding an endless supply of water that no one could drink. In the late 1990s, Israeli engineers proposed something that sounded more like science fiction than civil engineering. They would construct an enormous network of channels and pipelines to transport seawater deep into the desert's interior. Then, using advanced technology, they would strip away the salt and minerals, transforming ocean water into something pure enough to drink and farm. With the scale of the proposal was staggering, requiring billions of dollars in funding and construction methods that had never been tested in such extreme conditions. When approval finally came in the year 2000, with an initial budget approaching $3 billion, the project moved from concept to reality. But before the first pipe could be laid, the desert itself had to be conquered. Survey crews spent months mapping terrain that shifted constantly under wind and heat. They used satellite technology and ground sensors to identify stable zones where construction equipment could operate without sinking into loose sand. Every measurement had to account for temperature fluctuations that could alter the landscape overnight. Drilling teams bored hundreds of test holes, some reaching depths of 30 meters or more, to analyze soil composition and detect hidden weaknesses in the substrate. These investigations revealed layers of compacted sediment interspersed with pockets of loose material that would need reinforcement. The data collected during this phase determined where channels could be dug, where reinforcement was essential, and which routes were simply too unstable to consider. Once planning was complete, the physical transformation began. Bulldozers by the hundreds moved across the desert in coordinated formations, cutting through dunes and redistributing millions of tons of sand. The machines worked around the clock, their operators enduring conditions that tested both human endurance and mechanical limits. Dust storms could reduce visibility to zero within minutes, forcing temporary shutdowns that set schedules back by days. But leveling the surface wasn't enough. The sand beneath remained loose and prone to shifting. Underload engineers developed a technique using controlled water injection to bind sand particles together, forming a more cohesive base layer. Specialized vehicles equipped with spray systems moved along the prepared corridor, releasing measured amounts of moisture into the upper sand layers as water penetrated downward. It created temporary bonds between grains, allowing heavy compaction rollers to press everything into a dense, unified mass. The compaction process itself was methodical and slow. Each section of prepared ground received multiple passes from massive steel rollers weighing dozens of tons. The weight and vibration forced air pockets out and locked particles together, creating a surface firm enough to support concrete mixing trucks and excavation equipment. By the time each section was complete, the sand had transformed from a fluid obstacle into something resembling solid ground. With the foundation ready, excavation teams began carving the main channel itself. This wasn't a simple ditch, but a carefully engineered waterway with precise dimensions and slopes designed to move water efficiently without requiring constant pumping. The channel was shaped with gently sloping sides and a flat bottom, measuring roughly 45 meters across, a depth averaging 7 meters, allowed gravity to drive water flow over enormous distances. Every meter of this excavation was checked and rechecked by survey crews. Using laser leveling tools, the longitudinal gradient had to remain within incredibly tight tolerances. Just a few centimeters of error over 100 meters could disrupt flow patterns. Over 70,000 tons of material were removed daily from the construction corridor. During peak operations, the excavated sand wasn't wasted. Much of it was used to build up embankments on both sides of the channel, creating raised barriers that would contain the water once the system became operational. In areas where the soil proved particularly weak, engineers employed deep reinforcement techniques. They drove long columns of compacted sand or injected cement mixtures deep into the ground to create stable zones that could support the channel's weight and resist erosion. Over time, these interventions were essential for ensuring the system's longevity in an environment where a single structural failure could drain an entire section. Once excavation was complete, the waterproofing phase began. This stage would determine whether the entire project succeeded or failed. The desert sand's natural porosity meant that without proper sealing, any water introduced into the channel would simply disappear into the ground. Within hours, workers began by spreading and compacting a thin layer of fine sand across the channel bed and slopes. Then they poured concrete panels in manageable sections, each measuring roughly 5 meters by 3 meters. These panels were connected using expansion joints filled with heated bitumen, a material that remains flexible enough to accommodate thermal expansion while maintaining a watertight seal in zones where geological surveys had identified particularly porous subsoil layers. Additional protection was added in the form of high-density polyethylene membranes installed beneath the concrete. These plastic barriers provided a secondary line of defense against seepage. More than 350 kilometers of channel received this comprehensive waterproofing treatment, making it one of the largest sealed canal systems constructed anywhere in the modern era. Along the embankments, vegetation was introduced to anchor the soil and prevent wind erosion from gradually degrading the raised banks. But a channel alone cannot regulate water flow. The system required hundreds of control structures built at strategic intervals along the route. Reinforced concrete gates allowed operators to adjust flow rates, while spillways provided overflow capacity. Bridges were constructed wherever the channel intersected. Existing roads ensuring that the new water infrastructure didn't cut off surface transportation. In sections where the channel had to cross natural drainage paths, special culvert systems were installed, allowing seasonal floodwaters to pass beneath the artificial waterway without disruption. Distribution gates positioned every 10 to 15 kilometers enabled controlled release of water into secondary branch channels that would eventually carry it to farms and communities throughout the region. After more than a decade of continuous construction, the system finally reached a point where testing could begin. Engineers opened control gates, gradually allowing water to enter the channels. For the first time, flow rates were increased slowly over several weeks, giving the concrete time to cure fully under load, while technical teams monitored every section for signs of leakage or structural stress. When steady flow was finally achieved, it marked a turning point for the entire region. Communities that had depended on trucked water deliveries suddenly had access to a reliable supply. Farmers who had abandoned their land began returning and planning cultivation that would have been impossible just years earlier. Yet the water, arriving from the coast, remained unusable in its natural state. Seawater contains roughly 35 grams of dissolved salts per liter, far too concentrated for human consumption or agricultural use. The solution required facilities capable of processing millions of liters daily, using technology that could remove salt at the molecular level. The desalination plants built to support this system represent some of the most advanced water treatment facilities operating anywhere on Earth. Seawater enters through intake pipes positioned offshore where preliminary screening removes large debris. The water then passes through progressively finer filters that capture suspended particles down to microscopic sizes. The core technology relies on reverse osmosis, a process that forces seawater through synthetic membranes under extremely high pressure. These membranes contain billions of microscopic pores, each just large enough to allow individual water molecules to pass through while blocking larger salt ions. High-capacity pumps generate pressures exceeding 60 bars, pushing seawater against the membrane surfaces where pure water molecules are essentially squeezed through, leaving concentrated brine behind. The purified water emerging from this process is too pure for immediate use, lacking the trace minerals that give drinking water its natural taste. Automated dosing systems add back carefully measured amounts of calcium and magnesium, restoring a balanced mineral profile. Disinfection follows, using ultraviolet light to eliminate any remaining microorganisms, while a residual amount of chlorine ensures the water remains protected during its journey through distribution networks. From the desalination facilities purified, water enters the main channel system, beginning a journey that can span hundreds of kilometers. The entire process is monitored continuously by digital sensors that track salinity levels, pH pressure, and flow rates. Any deviation from target parameters triggers automatic adjustments, ensuring consistent quality. When water finally reached agricultural areas that had been dry for generations, the transformation was immediate. Farmers who had worked marginal lands with minimal yields suddenly had access to reliable irrigation systems that delivered water directly to plant root zones using drip irrigation technology that minimizes waste by releasing water in controlled amounts exactly where it's needed. Most, within a few growing seasons, tens of thousands of hectares that had supported only scattered desert vegetation were producing commercial crops. Orchards of citrus and stone fruit appeared alongside fields of vegetables, and grains regions that had been written off as permanently unproductive became major contributors to the nation's food supply. The visual contrast was striking enough to be visible from orbit. The economic impact extended beyond agriculture. Communities that had struggled with chronic water shortages saw their population stabilize and grow. Schools, clinics, and businesses opened in areas that had been considered too marginal for permanent settlement. The water infrastructure didn't just enable farming, it made normal, modern life possible in places where it had never existed before. Yet beneath these visible successes lie ongoing challenges. The energy required to pump and process millions of liters daily represents a significant operational cost. Desalination is inherently energy-intensive, and as demand grows, so do the financial and environmental costs. The brine byproduct from desalination also requires careful management to prevent ecological damage to coastal waters. Climate change presents additional uncertainties. Rising temperatures may increase evaporation losses from the channel system, while changing precipitation patterns could affect supplementary water sources. Engineers are already planning expansions and upgrades, but each enhancement requires investment and technical innovation. The story of this massive desert water system illustrates both the power and the limits of engineering ambition. Humans can indeed move water across impossible distances and transform its chemical composition to meet our needs. But we cannot escape the fundamental constraints of physics and economics. Every liter delivered comes at a cost. The desert didn't surrender. It was simply pushed back temporarily. So, the question that remains isn't whether this engineering achievement is impressive, but whether it represents a sustainable path forward. The answer will determine not just the future of this particular system, but the viability of similar projects being considered in arid regions worldwide.